Hey, welcome back from our break. It's been a quick 20-minute break here, and we swapped out the equipment. Let's finish up here with Chapter 11. A few more things to say here about Chapter 11, and then we better get started into Chapter 12. But I'll begin with saying here was the idea that keep this big picture in mind. It's called this kinetic theory, and that is everything is made up of these little atoms or molecules, if the atoms are hooked together, and they jiggle around. And so when you get it hotter, they jiggle faster. In fact, I was just outside and I thought I'd show you something real quick, but it's a nice warm day here in Santa Barbara, and it's warm because we have Santa Anas, and the Santa Anas are warm because it's high pressure and it's sinking down. And what ends up happening is as the air molecule comes down and sinks, the pressure squeezes it, and that actually makes it go faster. And I'm kind of hoping you can see that with maybe this ping pong ball here. If I do something like this and I just kind of bounce the ping pong ball, but if you can imagine me squeezing the ping pong ball, it goes much faster between my ping pong ball and the table as I drop it down. And so that's what's happening to the air molecules here. So the air molecules are another really good example today, and why it is warm today. Weather is a good example of using the ideal gas law and the kinetic theory. And so there's a lot we could say about meteorology. But as I said, we need to wrap up this chapter. So I'll continue here to talk about a few other things as we wrap up. But maybe one of the most interesting parts, and a big important one then, is we could use this whole idea that temperature is higher with higher motion, and motion needs thermal expansion to build what we call a thermometer. And so let's talk about, maybe right here would be a good place here. Let's talk about the three most common temperature scales. And I think you know the simple one, or maybe the one that you were introduced to first, maybe way back in kindergarten. And so Fahrenheit was the first scale. In the metric system, though, we like to jump over to the Celsius scale. So let's talk about that. That's a little better scale. And even better than that is the Kelvin scale, and I don't know if you have any background or familiarity with that one, but I wanted to emphasize that one. And so let's talk about these different temperature scales, and I'll begin with just their basic how do they work type thing. So I grabbed a big thermometer, which hopefully looks like a comparison of this brass rod that we used before the break. And so I was showing you thermal expansion with this brass rod and the needle. In fact, maybe I should grab the needle. There's some neat things to see about the needle. I just set it back here. This will give me a chance to come back to the needle here. But this thermometer works in exactly the same way. That is, down here at the bottom of the thermometer is a mercury. And if I were then to put this into, say, some hot water, the molecules of hot water would hit the glass first, and then the glass molecules would hit the mercury atoms, and then those would start moving faster, and then they would go up the capillary tube. And so that's why things up here represent high temperatures, and when the mercury is down here, that's low temperatures. And so we have these temperature scales, but the way we build a thermometer is to take advantage of the thermal expansion. And the mercury is really nice because it is a metal, it expands a lot, but it's also a fluid at room temperature here. And so this is our mercury thermometer. So again, putting together the whole idea of the kinetic theory, that is, the warmer they are, the faster they move, and therefore you'll have thermal expansion, we can use that idea of temperature and build a temperature scale. And Fahrenheit realized that. So Fahrenheit built the first temperature scale. Let me kind of represent it with a thermometer that looks like this. And you got to kind of understand his work for the scale to make any sense, because he was thinking about how to build it, how to develop it, and at this point I'd say how to calibrate it. And so if you could imagine this brass rod, and this is what he used. I'm not sure if it was brass. In fact, I think it was copper, but he used something like this with a rubber hose on it. And then over here, he had pots of boiling water and a pot of ice water. And the idea then was simply this, that if he set the ice water, or sent the ice water through the brass tube, and he made a little indication of that mark, and then he sent the boiling water through it, it would make the brass rod longer. And so it's real important to understand the Fahrenheit scale, to understand that he wasn't working with mercury at first. He was working with just a regular piece of tubing, a metal tubing. All right, so if you can imagine a rubber hose going over here, and I've got ice water running through it, and then this end over here is at this dial, and we put the dial maybe straight up to begin with. He says, all right, this is where it is when I have ice water. And then he lets the boiling water go through. And so like you saw in the previous video, the boiling water would make it expand. Now I made it expand a quarter of a circle. But he adjusted his setup so that when the boiling water went through, it expanded a half a circle. And the reason that's important then is because what he does, and it makes sense when you're looking at a dial, it doesn't really make sense when you're looking at a straight line, is he says, well, let's call that 180 degrees, 180 divisions, right? It's a half a circle. And what he meant by degrees was an angle. He didn't mean temperature. And so I find it kind of ironic today, because today we associate the word degree. If somebody said degree, you would pause and go, wait, degree, do you mean temperature or do you mean angle? And he meant angle, and it got associated with temperature. He was just building something that would actually change, and so he's got this half a circle. Of course, he doesn't stop there. He asks himself another question like, okay, what would happen if I got it colder than ice water? And he realized it's fairly easy to get something colder than ice water. I don't know if you've ever made homemade ice cream, but as you might know, especially if you made homemade ice cream, is that milk does not freeze at ice water. You got to get it colder than ice water. And so the way you can get it colder is by mixing it with salt. And so he knows that, and so he mixed it very heavily with lots of salt. And so I know when I make homemade ice cream, I put all the ingredients in the center container, and then on the outside I put a little bit of ice, lots of salt, a little bit of ice, lots of salt, a little bit of ice, lots of salt, and you stir it around. And as the salt dissolves, the mixture of ice, water, and salt can get very, very cold. So he tries that. And so let's come back to this needle. And so his needle, that I will say starts straight up right here at ice water. Then when he mixes it with the salt, the needle goes the other way. It contracts. And he measures how far it goes the other direction. And of course, since he's on a dial, that's the key. He's on a dial. He's not on a straight line. The dial angles back, and he goes, well, I wonder what angle that is. And he notices it goes back 32 degrees. So he starts his temperature gauge, if you will, his first thermometer, in terms of angles. Now, maybe this is the part that he really shouldn't have done. He said, let's avoid negative, so let's call the lowest angle, which is this ice water, let's call that 0. So he calls that 0 degrees Fahrenheit. And so that would make ice water then 32 degrees. Again, he's looking at a dial. He's not talking about a temperature, although that's what it's become. He's saying the dial would move an angle of 32 degrees if you warmed it up from ice water to, from salt and ice water to just ice water. And then if you warmed it up even more, you went from ice water to boiling water, it would go another 180 degrees, a half a circle. And if you add 32 to 180, you get 212 degrees. And so for those of you, especially for my international students, you may not have ever worked with Fahrenheit. This is our definitions of our different degrees. Boiling water is 212 degrees Fahrenheit. Ice water is 32 degrees Fahrenheit. And a heavy mixture of salt and ice water is 0 degrees Fahrenheit. And so this is his temperature scale. And like I said, I found it funny, he did not mean for degrees to really represent a temperature scale. But after he had built one with a dial, it wasn't long before he and others started building them in a straight line made out of mercury. And then even though it wasn't an angle anymore, it just carried along. And so because of that, the word degree became a double meaning. It means not only angle, but it also means the temperature scale. All right, well, Celsius then says that's probably not the best kind of scale we could have. And Celsius comes along with the metric system, and the idea of the metric system was try to simplify all these units so they'd be easier to work with, easier to know, and everything was a base 10. And it's much easier to work with in multiples of 10 than things like, you know, a foot is 12 inches and a yard is 3 feet and all these weird multiples. He said, let's just stick to the common multiples of 10. So Celsius does recognize that this markers of ice water and boiling water are excellent. He does say that the salt water is a terrible idea because it depends on what kind of salt it is, it depends how much salt you put in, and so let's eliminate that as a reference point because you know what I do in my lab might be different than you do, and so that's not good. But we can all make ice water and boiling water. I mean, boiling water is really easy. Anybody can take water, put a flame under it, make a fire, and it's consistent around the world. So the ice water and boiling water become excellent reference points, but the salt water doesn't. So he says, let's get rid of the whole idea of salt water. Let's just, and we only need 2 anyways, so let's just use boiling water and ice water. And because we're talking about multiples of 10 then, let's take the ice water and call it 0. And then let's take the boiling water and make it a multiple of 10. He could have called it 10, 100, 1,000, 10,000. And he chooses 100. He thought 100 would be a good number of marks. I guess 10 is not enough and 1,000 is too many. And the funniest thing I find about this, though, is even though he's trying to make it a base 10 and he's trying to make it a linear scale instead of a dial, he still calls it degrees Celsius. Degrees Celsius. And so if you're not familiar with the Celsius scale, although I have a feeling everyone is, but maybe not, ice water then is 0 degrees Celsius and boiling water is 100 degrees Celsius. And so that's kind of the difference between those scales. And of course, being part of the science and the metric system, we really do like and appreciate the base 10 a lot better. And so as you undoubtedly know, we're going to be using Celsius as our kind of our standard one. Although I will say Kelvin's even better still. So let's talk about that one in just a second. But I would say then there must be a mathematical conversion from one to the other. And it's pretty easy to kind of see that here. If I were to make a graph, let's say, where on one side I would like to put the Celsius scale, so maybe on the x-axis I'll put temperatures in degrees Celsius, and then the corresponding one on the vertical axis, degrees Fahrenheit, then looking at this connection of 0 degrees Celsius should be right there, 32 Fahrenheit. And so I'll put 0 Celsius. And over here, 100 degrees Celsius would be the same as 212. And there would be a linear or a one-to-one correspondence with that. And so this line, this mathematical line, would represent that, okay, if I had this temperature on the Celsius, degrees Celsius, I then would correspond to this 1 degrees Fahrenheit. And so luckily, that's a pretty easy equation to see the difference between them. I'll take you back to your algebra class. But your algebra class, you probably remember that y equals mx plus b, the equation for a line. So if we let x represent the temperature on the Celsius scale, and we let y be the temperature on the Fahrenheit scale, this would be our mathematical tool from going from one to another. So all I need to do is put in the slope. And so the slope would be the rise, which again from ice water to boiling water was set up as 180 degrees. The run, again, ice water to boiling water, was set up at 100 degrees for the Celsius. So the slope here is pretty easy. It's just 180 over 100. And the intercept is 32. And this then is the mathematical formula that you're going to need moving forward, that if I give you the temperature in Celsius, you can get it in Fahrenheit, or the other way around. If you know the temperature in Fahrenheit, you can get it in Celsius. And I like it in this form. You will often see this fraction reduced to 9/5. And the mathematician would probably like that, and the mathematics in me says, hey, let's reduce it. It's an easier fraction. But it's easier to remember when you realize it's just the rise over the run. It is just how much is it from ice water to boiling water on the Fahrenheit scale, 180, compared to what is it on the Celsius scale, which is a 100. So I prefer this form, and that's why I'm putting a box around it, but this is a little bit easier to calculate. But that aside, both of them are still just as equal. Now, let's talk about the third temperature scale. Kelvin comes along, and he too agrees that the ice water and boiling water that Fahrenheit originally picked is great. He also agrees that the salt water should be even considered anymore, as Celsius throws it out, so he won't even think about that. He also agrees that the metric system with the 100 divisions between ice water and boiling water is probably a better choice than a dial that is a half circle at 180 degrees. So he wants to keep the numbers between ice water and boiling water 100. But here's where he does two new things that are really very useful. The first one, and maybe it's not that useful, is he says, let's drop the word degree. The word degree is just wrong. Celsius should have dropped it way back when we left the idea of a dial, but since he doesn't, let's do it now. And so because of that, and it's really hard to say, you never say the temperature on the Kelvin scale is, like you would never say the temperature is 100 degrees Kelvin. You never use the word degree. You just say it's 100 Kelvin, or it's 200 Kelvin, or it's 300 Kelvin. And I must say, it is really hard for me to say that. You'll probably notice in the next couple of chapters, I'll keep messing up. I'll say, hey, let's take a temperature of 300 degrees Kelvin. Oh, I meant 300 Kelvin, because there is no degree, but it's so plugged into our mind. So that's one thing, and that's really kind of minor. Here is the biggest thing. the biggest thing is Kelvin takes a look at this 0. That Celsius said, let's call that ice water. And Fahrenheit said, let's call 0 just the lowest I can get it with the known technology. Both of those are not, in Kelvin's mind, and in my mind for that matter, not a good choice of 0. What Kelvin says, and I'll come back over here to our bouncing BBs, is that if you take something like this, where it's bouncing around, and if you're trying to say that if you warm it up, they go faster, okay, and if you cool it down, it goes slower, okay, slower, slower, he realizes that there is some point that if you got it colder, 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 they would come to a stop. And he claims, and I too claim, that a better scale would be a scale where somewhere, way down here somewhere, what we're going to call 0 Kelvin would be the point where the molecules come to stop. You see, what he's trying to do is he's trying to set up a temperature scale where the value on the temperature scale is directly connected to the motion. Because all the physics that goes on is related to the motion. The reason it gets bigger is based upon its motion. The reason there's more pressure is based upon the motion. And so his claim here, and I totally agree, that the best temperature scale we can have is one where the numbers on the scale are directly related to the motion. And so 0 on this scale. So 0 on the Kelvin scale must be the place where they come to a stop. We call that absolute 0. And so just that concept alone is really the great discovery of Lord Kelvin. Later on he gets lorded, so he becomes Lord Kelvin. And he realizes that there is what today we call the coldest something can get. You can go slower and slower and slower and slower and slower, but eventually you get to stop. And you can't go any slower than stop. So you can't get any colder than absolute 0. And so he comes up with this whole notion of absolute 0. And he comes up with the idea that we should build a temperature scale that is based upon motion. And that's why I say this is the best temperature scale, because it works best in our formulas. This temperature scale is really the key. And so he runs some experiments to try to find out, well, where is this absolute 0? I mean, how cold do you have to get? And that's the lab we're going to do today. And so when we're done videotaping here for this morning, this afternoon, I'll go into the lab and we will do what we call the absolute 0 lab. And that absolute 0 lab is a repeat of what Lord Kelvin did in order to find out how low this temperature is. Even if we can't get that low, that's kind of the neat thing. So I'll say more about that in the lab, but it's a neat experiment. We don't have to get that cold, we just have to look for the pattern. We have to start with things hot and then watch them as they cool down and get some different measurements as they get colder, and then just say, what if they continued? Then where would they come to a stop? So we call that extrapolating the data. And so it's kind of a really neat experiment today. And I wish you guys could be here and do it face to face, but we'll do it as partners together here when we get into the lab. All right, so I want to emphasize then, Kelvin then discovers A, absolute 0, and then B, makes a new temperature scale that has a lot of the same features as the Celsius scale with 2 important differences. One, he gets rid of the word degree, but more than that, he gets rid of where the 0 is. Or I shouldn't have said it that way. He puts the 0 at a better spot, a more appropriate spot. He puts the 0 Kelvin at the lowest temperature anything is possible. I suppose another way of saying that is he only has then positive numbers in his scale. And some people think that that's why it's called absolute zero. And that's really not a good definition. It's true that there are no negative numbers, so that's not so bad. But the real important thing is he realizes there is an absolute zero. He realizes there is a point that things cannot get any colder. And he wants to find that, so he runs some experiment. So we'll do that today, and hopefully we will find this. Hopefully we will find that this place is negative 273 degrees Celsius. And so we will run an experiment like he did. We will run the experiment using the Celsius scale. We will then see that if we could, because we can't get it this cold, the coldest we're going to be able to get it today is about negative 70 degrees Celsius. And the hottest we can get, we'll do boiling water. And so we'll make some measurements between boiling water at 100 degrees Celsius and some dry ice, which will be about negative 70 degrees Celsius. But we'll say here we got a pattern, and if we extended that pattern, we'll be able to see from our data that they would come to a stop at negative 273. So for class today, I'm just going to tell you it's negative 273, and then hopefully that will give you some insight that that is the difference between the Kelvin scale and the Celsius scale. And so if I kind of do the same thing here, that if I make a plot here, and say, all right, why don't I plot on the, I'll just do the Celsius scale here and the Kelvin scale here. And so 0 on the Kelvin scale would be way down here at negative 273. Since they have the same markers, if you will, 0 degrees on the Celsius should be 100 higher than 100 degrees Celsius, so I guess something like this. So an increase of 100 on the Celsius scale is also an increase of 100 on the Kelvin scale. That's kind of nice because that makes the slope of 1. And if we then have a connection and say, what's the equation of a line? Y equals to mx plus b. The slope would be 1. The horizontal axis would be the temperature on the Kelvin scale. The vertical axis would be the temperature on the Celsius scale. And the intercept would be negative 273 degrees. And if we simplify it, we could either leave it like this, although I kind of like it over here. So temperature on the Celsius scale, add 273, you'll get the temperature on the Kelvin scale. And so, again, this will be useful as we do the homework. If you ever have a temperature on either the Celsius or the Kelvin, you can then convert it to the other one. And of course, you can then also convert to the Fahrenheit, although I don't think we will do that much. Just because this is a science class, but in more of an engineering class or even a meteorology class, we would probably talk a lot more in the Fahrenheit scale. But we're probably going to talk about the Celsius, or more importantly, probably the Kelvin. And so 9 out of 10 times we'll talk about Kelvin, maybe 1 out of 10 times the Celsius scale, and then seldom on the Fahrenheit scale. So that's our temperature scales here. And so again, that's more of our ideal gas law. Finally, we can put together really the grand finale of all of this. And this is what we've been building up. But in the process of building up, hopefully we've given you some insight to this kinetic theory and things like thermal expansion and our temperature scales and how to convert from one to another. But if you remember way back before the break, I said there was an equation, an ideal gas equation that connects all of these together, the temperature, the pressure, and the volume. And now that we've spent a lot of time talking about them, hopefully conceptually you have that, because that will lead to our equation. And so let me just put the word here, pressure, and then come back over here to our little bouncing BB experiment and say, all right, if I turn this on, and this is my gas molecules, this is the bouncing BBs, this is what we call the ideal gas model, there then should be an equation, which we will call then the gas law, or the ideal gas law equation, that connects what is its temperature, what is its pressure, what is its volume. Because you can even see this. What do you think would happen if I warmed it up? So I did this. See how the volume changed? Or what if I did this? I push it down and make more pressure. See how its volume goes down? That thing's loud. Okay, but there is then a mathematical connection between pressure, temperature, volume, number of atoms, anything else. And that's what this was all building up to. And maybe you can see it this way. And I shouldn't put equal because you're going to see that's not quite what it's equal to. But let me put a capital P for pressure. And I like to say this. If I come over here and begin to say, what is causing the pressure? One of the first things that I see here is the speed of those molecules, those BBs. How fast are they going? And so the more speed or the more temperature, the greater the pressure. And so sure enough, I would say one of the factors is its temperature. And with that said, the temperature on which temperature scale would I use? Would I use Fahrenheit? Would I use Celsius? Or would I use Kelvin? And I hope what you got out of that discussion just a moment ago is it would be on the Kelvin scale, right? See, the Kelvin scale is the only one where the numbers on the scale are directly related to the motion. And it's the motion that causes the pressure. And so let me emphasize by putting a little sub K down here that I would think the pressure would depend upon temperature, but only when I use the Kelvin scale. This would not work on the Celsius scale. This is kind of my hint towards you because it's a very common mistake that students make in this chapter when they do the homework. It's also a very common one they make when we do test number 2, is they tend to use the temperature in Celsius. So take this as my warning. This, as we derive this equation, it is not the temperature on the Celsius scale. It is not on the Fahrenheit scale, although students don't usually do that. But they do it on the Celsius scale, and that's just not appropriate. The Celsius scale is not a scale that the motion is connected to the number on the scale. Only the Kelvin scale is. So one of the factors would be its temperature, but only if we do the temperature in the Kelvin scale. All right, what else do I see over here? Well, hopefully what you've seen after this last hour of watching and showing and talking, that the other reason there would be pressure, remember the first one is motion, that's temperature, but wouldn't it be how many are hitting the surface? So it's not really how many atoms, but it's really the concentration of the atoms. You know, what I mean by that is it would be the number of atoms per volume. See, because if I just had a bigger container, if I had this giant, enormous container, I might just have more molecules in there, but that doesn't mean more of them hit in a little small area. Remember, pressure is the amount of force per area. So it's not really the total number of atoms, it's the concentration of them. And so you could think of this as two factors, and so far we would have a total of 3, but I like to think of this as two factors. I like to say that the pressure of an ideal gas is coming from 2 reasons. Number 1 is, how fast are they moving? And number 2, how concentrated are they? Now, of course, concentrated is actually 2 factors in itself, so you may think of it as 3, and you're entitled to do that. But I think it's easier to think of it as 2 factors. 1 is, how fast are they moving? And number 2, how concentrated are they? Now, to make them equal, there would be some multiplication constant. In math class, we would call this a proportionality constant. And so if I put this in symbols, some of you are probably beginning to recognize this from maybe a high school chemistry or even a chemistry that you took already here at City College. But I'll have a P on this side. We like to use the symbol T for the temperature. Now, the number of atoms goes back to earlier on in this chapter. Instead of me saying the number of atoms, let me say the number of moles. And so I'll pause again here. We talked about moles. Remember, moles is just a grouping. And so we could say that there are 16 days before the end of the semester, but we could also say that there is 2 weeks and 2 days. And so we can group it. We could also say, hey, I'm going to go to the store and get 24 donuts. But it's a little better to say, no, I'm going to go to the store and get 24 donuts. Okay? And so let's do that same thing here. Let's not say how many atoms do we have. Let's say how many moles do we have. And the symbol we're going to use is the lowercase n for that. And then we, of course, have the volume, which is the capital V. And then, of course, we would need this constant, and so we call this then the gas constant. It's a number that, to make it proportional, we would probably just go into the laboratory and make some measurements. And the traditional choice has been R. If I rearrange this equation, it'll look like its more popular form, if you will. PV equals to nRT. I'll put a box around that because I have a feeling that a lot of you have seen this equation, PV equals nRT. I prefer to kind of show it how it is derived. If you